And so we're going to welcome back Amnon Potashik, who is Allotrope's technical director, and he's going to be talking about a sort of larger deep dive, I guess, into the Allotrope simple models, especially focusing on validation and on demonstrating their use.
Hi, good morning, good afternoon. So this is the second part of the introduction of the ASM, and we will dive in directly into the JSON schema primer, which was derived from the jasonschema.org. So we'll start with the why do we need actually validation. So JSON schema is a vocabulary that allows the annotation and validation of JSON documents. With JSON schema, we can provide detailed description for data format, provides clear, human-readable machine and documentation, and it validates the data, which is useful for automated testing. And in the client-server architecture, it's ensuring the quality of the submitted data. Now, there are content consumers and content producers. So why do we need to formalize the description? For the producer, they can get clear guidelines. The distributed content structure is unified and interoperable, and this content distribution can be associated with this structure. On the other end, for the content consumers, they can get clear guidelines on the expected structure. They can verify it prior to processing it, and the expected structure is unified and interoperable. So for diving into the JSON primer, let's take a use case of a lab instrumentation inventory record, where we have the data instance in green and we have the JSON schema in yellow. And the data instance is a very simple data instance. We have instrument ID, which is a 45, and the instrument name, like a benchtop refrigerator. The operational status is true, and it's applicable for research and clinical in our inventory. So JSON schema is a property called keywords, and keywords are expressed as JSON key. There are the schema keywords, such as $schema and $ID. The $schema specifies a standard for version and useful to draft the document and provides version control. And the ID, as it sounds like, it's for identification, and it also serves as a base URI for relative references of keywords within our document. And the annotation keywords are for descriptive only, and they do not add any constraint to the validated data. So title and description, and in this case, we have very simple title, instrument, and the description is an instrument in the laboratory. And the interesting part is with the validation keywords. And the validation keywords are for setting up the constraints. So the first one is the type validation keywords, which defines a constraint on the JSON data. In this case, it's an object. So the instrumentation object is type, as we can see, key value, name value, per type object. And then we have properties. The properties validation keywords define constraint on the JSON data properties. So in this case, we have the property of instrument ID. We have the description just for our information only, and the type, the constraint on the instrument ID that it needs to be integer. And then we have the required keywords, and the required validation keyword defines a list where every item in the array is a name of a property in the data instance that need to be present, which practically enforce the existence of the property in the data instance. In this case, we have the required instrument ID to be present in the data instance. So let's increase the list of the requirements for the required properties, such as instrument name and operational status. So we add to the list the instrument ID, to the initial instrument ID, we add the instrument name and the operational status, so that we ensure that those properties are existent within our data instance. Now let's add additional constraint on the properties. It makes sense that an instrument ID is an integer value with which is greater than 0. So we are using another constraint keyword, which is exclusive minimum 0, which ensures that the instrument ID is a positive number which is greater than 0. And there are some other validation keywords for numeric or integer numbers, such as multiple of maximum, exclusive maximum, and minimum. Let's deal now with the tag properties. Let's assume that the following requirements on the instrumentation tagging. If there are tags, there must be at least one tag. Tag must be unique, meaning no duplication for a single instrument. Tags must be in a text format, and tags are nice to add, but they are not required. So those requirements are translated into tags. We have the description, which is just for our information only. Type, it's an array, and the items are strings, meaning the type of the items within the list is a string. The minimum items is 1, and the uniqueness of the name is unique items equal true. But we are not including the tags in the required field, which means it is nice to have, it's not a required property. Now let's add a little bit of nesting within our data instance. So we're adding dimension to the instrument, length, width, and height. So we add the dimension key is added to the data instance. So therefore, the dimension key is added to the schema with the type validation keyword of object. So we have dimension with the type object. And now the properties are nested within our JSON schema for length, width, and height, and they are required within the nested object, not in the general object, but within the nested object and not the parents object. And each one is a type of number. So we can deal also with nested objects. Now, we can also reference with JSON schema, we can reference outside JSON schema, and it allows the decomposition and the modularization of the JSON schema. By having reference JSON schema in our parent document, we can minimize the verbosity of our original document. The reliability is enhanced since it is structured and modularized. It reduced the maintainability since some changes that we are making to the reference schema doesn't affect the parent schema, and it increased the reusability since the reference schema can be utilized by many other schema. So in general, it is a good practice to share JSON schema across data structure. And here, in our case, when we add the lab location, we are a lab location object. We are referencing to a lab location for JSON schema validation. We are adding a reference. This is the reference ID, geolocation schema.json, and also description for our information only. So let's look at the reference schema. The reference schema has an ID, which match the exact URI of the reference schema, and it has a title and a description for information, and the required field. We need both the latitude and the longitude. It's a type of object with property, latitude type number and longitude type number with minimum and maximum of -90 to 90, and as well as for the longitude. So this is our complete data instance for validation. Now we have we started from the original data instance, which has the instrument ID, name, operational status, and tags. We had a 2 nested object for the dimension and the lab location. And now we have the JSON schema to validate this data instance with a reference JSON schema for the geolocation. So now that we are expert on JSON schema, we can go into the quick overview of what was covered in the last presentation. The Allotrope simple model is a text representation of the Allotrope tabular models using JSON, and it uses the AFO, or the same ontology that we're using for the ADM, and leverages the ADM that was already defined and governed by the subject matter expert. And when we are saying it leverages the ADM, it means that the ADM is a pre-existing condition for the generation of the ASM. As we're going to see, the ASM is generated out of the ADM. And this is a reduced column set of the original Excel spreadsheet that is used by the modeling working group. We have 3 columns. The one is for the pref label of the parameters. The other one is a column is an example of a parameter value. And the third one is the parameter unit symbol. And this is an example of the conductivity tabular model, which has unique AFO terms within the Allotrope ontology, and it's perfectly aligned with the requirement for uniqueness of names within a JSON object. So like we have a unique AFO terms, we need to have within a JSON object, we need to have a unique name. So we plug in order to have the ASM data instance, we plug in those 8 conductivity rows within the Excel spreadsheet, and we get the actual ADM, the ASM data instance. So we have measurement identifier and its value, measurement time and its value, analyst and its value, and the actual result, conductivity value unit, temperature value unit, 28.6 degrees Celsius. But we have additional 2 lines, 2 properties within our JSON document. The first one is a free text comment, conductivity ASM. And the second one is the most interesting part, which makes the linkage to the ADM between the ASM and the ADM, which is the ASM.manifest. So if we look at this key value, this property of the ASM.manifest, we see the URI for the conductivity manifest, which provides the model identifier, the reference to the ADM, the vocabulary, and the JSON schema for validation. So we are looking at the manifest for in JSON format for the conductivity ASM. So we see the identification, which is conductivity.manifest. We see the type, it's a manifest file. We see now the shape file, which was defined for the ADM, the shackle shape file, conductivity.shape, and we see the vocabulary, and we see the related JSON schema for validation, conductivity.schema. So this is the linkage. It is important to understand. This property is the linkage between the ASM and the ADM that allows us to do the transformation back and forth, as we're going to see in a moment. So let's talk about a little bit about the ASM JSON schema. The Allotrope simple model are reference JSON schema for validation, as we mentioned, and they are using the latest specification, which is December 2020. And while Shackle, the shape constraint language, is used to validate ADM, yes, we are using Shackle to validate ADMs. We're using JSON schema to validate ASM. So JSON schema to validate ASM, and the ASM is transformed and generated by a transformation tool from ADM to ASM. Unlike Shackle, JSON schema is not semantically aware. And in order to maintain the Shackle semantic constraint available in the JSON schema, and to help with the transformation process from the ADM to the ASM, the JSON schema contains some Allotrope specific annotation, and those annotations are starting with the prefix of $ASM. And the generic JSON schema tools will, and they can also ignore this annotation. So this is very important to mention, that our JSON schema include special prefix $ASM that maintain the semantic compatibility to the ADM. As we saw in the reference earlier, the JSON schema allows for the modularization and factoring out some commonly used rules by utilizing reference to other JSON schema. We're using the same technique when we are defining our ASM JSON schema. So we have a core schema which contains reusable and domain-independent rules. And we are using technique-specific schema that contains the domain-specific rules. And having those basic rules factor out in a core schema allows for later extension without changing any specific within the technique specific schema. Let's discuss a little bit the generation and transformation tool. So within our modeling working group, we mint the terms and we are structuring the ADM. And we have a governance tool, which is the transformation tool, ADM to ASM transformation tool, to produce the ASM. So once we are defining the ADM in Shackle, we have a tool to produce the ASM that are producing JSON schema, and it's a one-time process. So it's a governance tool during the governance process. And how do we maintain compatibility? So we start from the ADM, while Shackle, as we mentioned earlier, Shackle is used to validate the instant data, which is defined in RDF. This is an input to the transformation tool, and the transformation tool produces the ASM while maintaining semantic compatibility, as we saw within by maintaining the manifest file and the other reference prefixes. So we can actually go backwards and produce from the ASM the ADM. And the JSON schema that is produced is used to validate the JSON instance. So bottom line, we are getting model consistency and data and semantic context compatibility. And we can actually go back and forth between the ADM and the ASM. Last but not least, the transformation tool architecture, a little bit about it. It's written in Java, and it has a common pattern model representation. So we have a common pattern model representation that we can go back and forth, read and write with a Shackle definition for our ADM, and we can go back and forth with our JSON schema definition for JSON data instance. So we can get a round trip from JSON schema to the Shackle file, and from the Shackle file back to JSON schema. And with this introduction, I will hand off to Ben to do a hands-on demonstration of the schema and the tools.
Thanks, Amnon. So yep, I get the fun job of showing the work in progress and hoping that it works. So bear with me for a second while I hit the share button. Everyone can see my screen okay, I hope?
Yes, we can.
Wonderful. And of course, it puts it on exactly the two wrong screens. I don't do PowerPoint often enough to get this right. So, I'll just, there's only a couple of slides, so I'll just very quickly run through here before we go into the interesting stuff. So just a quick reminder, some of the high points that Amnon mentioned, but I'll just reiterate for context for those who are maybe less familiar with Allotrope's existing technology stack. We have this concept of the tabular or the aggregation model. It's largely a set of key value pairs. The aggregation allows us to sort of aggregate these key value pairs within concepts like a collection, so a peak list, which contains a set of peaks, or facets or attributes of some other concept. So retention time, description, peak index, things like that would be attributes of the peaks within that peak list. So that's the overall, a very, very high level description of the structure of the aggregation model. Those are represented within the ADF files with the RDF triples within the data description. And the modeling working group, which is the main producer of these aggregation models, uses the Excel spreadsheet as a tool to create these aggregation models. We have a tool chain that can take a properly formatted Excel and generate the necessary artifacts. So yeah, a quick overview. We have this Excel template that shows the various bits that are needed, including the hierarchy and the data cubes, if there are any. So yeah, a very quick overview, because what we want to do is get to the interesting stuff, the actual demonstrations. So that's all the slides, I promise. We'll go to the actual content. So just as a quick sort of run through, the model that we'll be using for the demonstration today is the FTIR model that we've already released for the ADM tabular model. The Fourier Transform Infrared, I believe, is what it stands for. As Amnon mentioned, as I just mentioned, the modeling working group generates these Excel spreadsheets, and from this we can basically get the relevant terms, the pref labels, as mentioned, the IRIs, the actual unique machine identifiers for the terms. We can tell whether something is required or optional, and we have the actual example values. So from this, we generate the shackle shapes and the instance data that's used in the Allotrope data models. So I'll quickly jump to those. Again, just as a background, so we have an existing tool chain that uses that Excel sheet to generate these constructs, and we have the necessary shapes underneath. So a well-formed FTIR dataset must have a measurement time. The measurement time must have a value of date timestamp, and it must have a equipment serial number, and so on and so forth. So here's the shackle constraints, and this is what's used to restrict to control the content in the semantic form, the ADF form. Likewise, we have the actual data, as we've seen a couple of examples earlier. It's currently represented in Turtle, and it's a little verbose for those that aren't comfortable with sort of semantic technology. It does take a little bit of getting used to, especially with the machine IRIs rather than human readable terms. So the intent of the ASM is to make that simpler. I just wanted to show you these to give you an idea of where we're coming from. So the next step is the tools. So as Amnon mentioned, we've commissioned some tools to actually do this conversion from one to the other. So I've got two tools on the screen at the moment. Well, two tools on the screen that I'll go through, and then a quick demo of the outputs. So this is the schema converter. It is the tool that actually takes the shackle that I just showed you and converts that into JSON schema. So I could scroll through the content, but that's not the interesting bit. Everyone wants to see it run and probably fail because it's a live demo, and that's how these things work, right? But just to show you, it's set up currently so that it should take the file as an input file, the FTIR shapes that I just showed you, and then output them to FTIR.schema.json, and then the flag stj at the end is literally just to say convert schema to JSON. So now there's a magic moment where I hit the button and it goes wibbly. Or if I'm really lucky, it finds all of the shapes and then does the conversion for us. So you can see this folder, which I should have mentioned before was empty, now has this FTIR.schema.json in it. And if I open it up, we have schema. It should look reasonably familiar since it's pretty similar to what Amnon was showing earlier. We have these ASM property class and ASM pattern terms that he mentioned that help us to keep the mapping between the username, or the pref label and the machine readable IRI. So that, because that's stored in the schema, we don't have to worry about managing that on the data side. We know that we can translate that and keep that centrally. We also have these external references that were mentioned. So the core schema provides definitions for something should be a string as opposed to something should be a quantity value with nanometers as a unit, for example. Unfortunately, because this is still a work in progress, the infrastructure is not currently in place here to actually resolve those. So I'm going to do a small cheat and just copy in the necessary definitions that are used in this file. So things like the nanometer definition are now present in this file, and then just do a quick find and replace just to show that these now become local definitions, hash /defs rather than the Perl Allotrope. So the file is freshly generated, and literally all I've done is copy that content in. But that's generating the schema. So we have a tool now that can generate these JSON schemas out of the existing shape files. It's still work in progress. There are still some edge cases that don't necessarily work fully, but we're working on that, and it should be ready to go in the not too distant future. That's all well and good, but we also want to be able to do stuff with the instance data. So that brings us to this second tool, so RDF to JSON. So in the same way that the schema converter converts the JSON schemas to, the shackle to JSON schemas, this runs over the RDF, the turtle representations, and converts them into JSON, following the patterns that we've laid out for these different constructs, though the leaf nodes, the aggregate terms, the collections, and the facets. We have defined JSON schema approaches for those, JSON representations for those, and this tool then does that conversion from the turtle file to those JSON structures. Now this one actually runs over the entire folder rather than a single file. So again, it just takes the whole test folder that I've got prepared and just spits everything into output. And as I said, this one is also a work in progress. So it takes all of the files. You'll see a few errors popping up because some of the edge cases haven't been fully implemented yet. But it runs through, converts everything, and we should find that aside from these edge cases that aren't fully implemented yet, we have files underneath, including FTIR.json. A little bit ugly because it puts it all in one line. So let's do a quick format to make it a bit more readable. And we have, I would say, a fairly nicely represented JSON file. So we can see that an analytical method identifier has this value. The batch identifier is a batch number. It passed its conformance assessment. It is a beam splitter of these types. That possibly should be a single one of those types, but I think the example included a few examples. And then we have an infrared document containing the measurement document, the data cubes, so on and so forth. It contains another background document with a whole bunch of stuff. That's the converted data. So we've just managed to live, without hopefully too many errors, convert the schema and the data set for the FTIR that we've got. Now the last step is, does it work? Which is always the interesting piece. No, wrong one. So if I take ttl.json into this, for reference, this is the Newtonsoft JSON schema validator. So this is an online free tool, not something that Allotrope's created and provided. It's just one of the free online tools to validate JSON schema. Newtonsoft, for those who are familiar with C# will be a very familiar company, given they produce one of the most popular, if not the most popular, JSON library for .NET. So it's a pretty well-established name, but there are plenty of other alternatives. This is just one of the nicer, prettier versions that we've come across. One of the nice things, it's really a live process. So if I copy in the schema and the JSON, no errors are found. JSON validates, which is kind of what you'd hope for, given we've just generated. But let's make sure that it's actually working. So let's say this data cube, the wavelengths, let's call it one reciprocal meters rather than reciprocal centimeters. Oop, doesn't like that because that's not the unit that's specified for it. So a sample absorbance spectrum should have a unit of 1 over centimeters. The 1 over meters doesn't match that. So if we go back to centimeters, it's happy. So the schema is correctly checking units of things. Let's change a few other ones. Unitless, yeah, that unit S is definitely not a valid unit here. Likewise, Amnon mentioned that things are required. So we have a few examples of, let's see if I can find something. Too far down the file. So I know for a fact, for example, that resolution is required for this. So if I delete that, it's not happy. Just like the shackle examples that we have, it will tell us that resolution is required, and this is missing because it's specified in the schema. So until we put it back, it says, yeah, okay, that's fine as long as it's there. On the other hand, items like, say, conformance assessment, I believe, is an optional in this one. So if you don't include the optionals, that's fine. As long as the mandatories are present, JSON Schema will tell you off. So yeah, so it looks like we've been able to translate a shackle structure, a shackle constraints for the FTIR into JSON Schema. We've been able to translate the turtle file from the turtle example that we had into JSON, and we can see that it's with that minor tweak to make sure that the references are provided locally, pending the upload to Perl. We can see that it actually validates quite happily. So I think that's pretty much the summary of what I was going to show you. So we've got the aggregation conversion, we've got the schema conversion, and the validation in action. With that, thank you for your attention, and we are open to any questions or comments we might have.
Great, thanks Ben, and thanks Amnon.